All right, good morning. It's a pleasure to welcome you back to the second session, and I'm happy to call for the first talk, What Makes the Difference in Perovskite Oxides, by Annette Bussmann-Holter. Hello. Hello?
Okay, good morning, everybody, and thanks to the organizers for keeping up this conference, running this conference. It's amazing. It's now, I think, about 28 years, 28th time, or how often is it? It's true, yeah? Typically, I end up in a snowstorm coming to these conferences, and we don't know what's going on until Thursday or Wednesday, so eventually it ends the same as always. So I'm talking today about perovskite oxides, and of course everybody is familiar with these types of crystals and systems. But the question still remains, what makes the difference? Why are some of these oxides ferroelectric? Why are others not? Why do they undergo rotational instabilities? Why don't others do that? And so what I did, I started from a very systematic approach. So I said, I will just keep the BO3 unit intact and compare by replacing the A side, the dynamics of these systems to each other. On the other hand, if I find time, I will shortly talk about the reverse process. I keep the A side the same and change the B side. So this should tell you or give you some information what is going on in these perovskite oxides. So this is what I just said. And typically what you do, so there are many approaches like that, but the simplest one is based on Goldstone, Goodenough, Glaser, and all these people, that they say the tolerance factor is a decisive quantity to differentiate between the ground state properties. The tolerance factor is familiar to all of you, and in its most simple form, it says if the tolerance factor is less or equal to 1, the system should be stable and not undergo a ferroelectric instability. However, if the tolerance factor is bigger than 1, it is expected that the system undergoes a polar instability. But this is just not true in these compounds, as you can see here. Only barium titanate fulfills this condition, while lead titanate is ferroelectric and T is smaller than 1, and these two are not ferroelectric and have T approximately equal to 1. So this is an approach to try to figure out what is the relevant quantity in deciding about the ground state properties. This is just a very, very short summary of the properties of the compounds I'm talking about. So barium titanate is, as everybody knows, is a ferroelectric below 400 K approximately. It has long been debated to be either order disorder or displacive ferroelectric because there's a soft mode, a transverse optic soft mode, but simultaneously, local dynamics shows that there must be some order disorder component. And there were recently a couple of papers which showed that you have a coexistence of order disorder and displacive character. PTO has long been believed to be the classical soft mode driven displacive ferroelectric, but also again recently XFs and XANES results, NMR and all these local tools showed that there's also an order disorder component in this crystal glass. CTO is the eponym for perovskites. It was discovered a long time ago and by somebody, this doesn't work properly, not by Perovsky, but Perovsky made it famous, but by this German mineralogist Gustav Rose. And this is, of course, intensely investigated, undergoes various phase transitions, but never turns ferroelectric. Then I go to further perovskites, titanates. Strontium titanate, everybody knows, is, I think, the best investigated perovskite at all. It is well known for its interfacial properties, for superconductivity as a layered material, so it is well investigated. And even nowadays, if you look up the citation of strontium titanate, you find at least something like 10 papers per week on this compound in all its different modifications. Europium titanate is antiferromagnetic below 5.5 Kelvin. This is known since about 60 years almost. And it was supposed to be very boring until we found out that until the group of Stanislav Kamba and the Czech group found out that a dielectric anomaly with a drop of 7% it can be related to a soft mode. And from then on, it was in the intense research due to the fact that it could be a low-temperature multiferroic. But this is not the issue. So I go through this only very quickly because there are too many papers on these perovskites, so I really cannot cite everybody and all the papers, but I'll just give you a short outlook of the papers. So first thing is, of course, to look at the electronic structure of these compounds and compare them to each other to figure out is there a signature in the electronic structure which can differentiate between all these 5 different titanates. And if you look at it in detail, then you see more or less they all have the same features. Oh, yeah. You have the p-band being the valence band being dominated by p states, oxygen p states in all these compounds. There's an admixture in lead titanate from the lead s bands in the valence band, and the conduction band is dominated by the d electrons. The bands, the only exception is in europium titanate. You have a very, very localized band from the F electrons sitting in the band gap. If you look at the pure band gaps in all these 5 compounds, they are more or less the same. There's something in between 3 and 5 EV, so there's not something which would tell you this compound is a ferroelectric, the other one is not a ferroelectric, if you look at these band structures. So we looked at another series of compounds just to compare these two to each other. That is what I said in the beginning. We exchanged the B-side ion, so the transition metal, to figure out whether this one is a driving force. So we kept the A-side intact and modified the B-side, and then compared these 2 series to each other. We took the lead transition metal oxides, but you can do the same for the series of, for instance, barium, titanate, hafnate, and zirconate, europium titanate, zirconate, hafnate, etc. So the trends in all these families are the same, and you can somehow generalize what is coming out for this series. So these are well known. So you have in all these compounds, you have also transitions from cubic to lower symmetry. Lead titanate is the only one which is ferroelectric at rather high temperature. Lead zirconite undergoes 2 transitions, which are to an antiferroelectric state rather similar to lead hafnate, whereas lead zirconite, one transition is a little hidden below the other one. I think we will hear about this later on. So these transitions are almost on the same order of magnitude and all are going to a polar structure. So again, common are the features that the B ion is left intact, and as I said, the B ion itself doesn't change the transition series in these compounds. So I come to the band structure. Here lead titanate is compared to lead zirconate, and here you have 2 different methods of evaluating the gaps in the hafnate. But again, what is obvious in all these series is that the valence band is dominated by the p states of oxygens with admixture of the s states of lead. And again, the conduction band is almost exclusively made up of transition metal D states. The band gap, and this holds for all these compounds where you keep the A side intact, the band gap is systematically growing if you replace titanium by zirconium by hafnium. But this is, you can follow it through all 4 or 3 series which are existent, but this is due just to the fact that you have a bigger volume and the D states are more expanded if you go to the higher homologs. So again, from this data, this is reference to the work, so it's really a lot of work being done on all these compounds. So what we did from the very beginning, we calculated the double wear potential in the titanium or transition metal oxygen interaction, the PD hybridization effect. And what is a self-consistent calculation, so it is parameter-free. And what is entering in the calculation is this average distance titanium oxygen in all these compounds. What is now very evident from the very beginning, this is europium titanate. It has a very narrow potential, rather deep, and so there is almost no room for the transition, for the PD hybridization to become effective. If you go to the next compound, this is calcium titanate, you see it's getting broader already. So this means you have a trend to delocalize and hybridize PD states of oxygen and then transition metal. And with respect to strontium titanate, it's getting even broader. But they're still shallow, so this indicates that you're far away from a real ferroelectric or polar instability. Now, if you turn to lead, this is the blue line, you see it's still rather small, so not far extended, but I have to add here that in lead titanate you have to take into account the lead-ion polarizability, so that the potential differs caused by this lead-ion polarizability. Now we come to barium titanate. This is this broad potential, so very broad and very steep, and what came out from the calculation is that barium titanate can as well be described by this dashed green line here, because it has a first order transition. So this shows up in the fact that the dynamics can be modeled by two kinds of potential. But in the following, I just take this broad double wear potential because it doesn't make a big difference for the dynamical properties. But you have to keep in mind that the transition in barium titanate is first order, and this is reflected in this dashed potential shown here. So the first thing which we did is to calculate self-consistently the soft optic mode, which is common to all these 5 compounds. And what people easily and often overlook is that the soft optic mode is coupled to a soft transverse acoustic mode at the zone boundary. So if you look in experiments, then you see that the optic mode, the polar ferroelectric mode, causes an acoustic mode to soften simultaneously, but much less than the transverse optic mode. And so I compare here the 2 modes. So this is lead titanate. The full symbols refer to the optic mode and the open ones to the acoustic mode. So you see that this mode drives also some mode which is caused by rotational instability. This is more obvious in barium titanate, where you have a mode crossing. So you see that first the acoustic mode is much softer than the optic one. Then there's a mode crossing, and this has consequences for the precursor dynamics and the formation of polar nanodomains. Now these two can be compared much more easily because they are all incipient ferroelectrics and they all have a soft mode. But what is obvious from the very beginning is strontium titanate tries to become a ferroelectric, as everybody knows, in the vicinity of 20 Kelvin, but then quantum fluctuations stop it from softening completely. Now looking at calcium titanate, it has the same tendency, but if you extrapolate the optic mode to 0, you end up at minus 40 K. So this means the system is further away from any ferroelectric properties. And now I come to europium titanate, which is the blue lines, and you see it does the same as strontium titanate, calcium, and calcium titanate, but the soft mode stops at around 6 MeV, 6 terahertz squared, the soft mode squared, and it cannot go to 0 at any finite temperature. So from this behavior, this has been called quantum paraelectric. I would say this is not a quantum paraelectric because there are no quantum fluctuations to stop it from softening. it would in no case go soft at a finer temperature. And the same holds for europium titanate. What is also clear from this, that you have again this crossing of optic and acoustic mode as a function of temperature. So this might be the origin, especially in europium titanate, why your group has seen this extra mode, you call it extra mode in the dispersion, which shows up below 200 approximately, as far as I remember. So this means that you have this mode goes back to the zone center below the structure phase transition. So you might observe an extra optic mode in the dispersion of europium titanate. Now I come to the dispersion of all these compounds, and you see striking differences in these dispersions. So this is lead titanate. I put in some experimental points, and you see the softening of the optic mode and the simultaneous one of the acoustic mode, which I just plotted before in the slide before. What is really striking is barium titanate. You see that it is almost dispersion-free, the optic mode at high temperature, and only gains dispersion if you go to lower temperature. Strontium titanate looks well behaved, the same as calcium titanate, and what is different again is europium titanate. Now I draw these red circles into the dispersion because I wanted to attract your attention to the fact that optic and acoustic mode are interacting with each other at low Q values. So you see here directly, if you look at the open squares, that this mode gets affected by the optic mode. This means you get a softening at finite Q, which tells you that you have a softening on the dimension of a couple of lattice constants. So this could give rise to polar nanodomain formation or elastic anomalies. If you look at barium titanate, then you see here is no something like precursor dynamics, because there's no interaction with the acoustic mode. Only if you come close to the phase transition temperature, then you can imagine that you have polar nanodomains or elastic nanodomains coming into the play. In strontium titanate, it's very much like in lead titanate. There's easily the possibility for interactions between the two modes, which is less given in calcium titanate and absent in europium titanate. So if you look at the elastic constants of these systems, you can immediately draw conclusions about the elastic constants, because this must be a very hard compound, very stiff. And this has been also seen experimentally, because below the structure phase transition, you should see the domain formation, and these are not easily movable, so they're very hard. And here you have the same behavior. Again, there's almost no interaction, the system is very hard, whereas these two others show different behavior. In order to look at the local dynamics, 2 minutes, okay. So we extracted from this something like elastic polar and polar nanodomains by looking at the interaction at small Q values and evaluating this as a function of temperature. So you see europium titanate is anomalous at the zone boundary because you have the spin-spin interaction for the antiferromagnetic ground state. So this is more or less very boring. If you go to barium titanate, you see the elastic anomalies are going to zero, to the long wavelength limit, so it deforms indeed, so, which is obvious from this figure. Calcium titanate remains on a long wavelength limit, but it does not show a homogeneous state. Lead titanate also goes to a homogeneous state, whereas strontium titanate remains in this clustered state. And here's the volume fraction, and you see it's diverging for lead titanate. For strontium titanate not, it remains finite if you go to t equals 0, but it's also diverging for barium titanate, whereas these two other compounds are more or less rather boring in their dynamical behavior. So we did the same for polar nanodomains, and Q actually tells you about the length scales of these nanodomains, and again, europium titanate is at its own boundary, so each second unit cell is affected by polar distortions, but it is not effective if you look at the volume fraction for these distortions. Calcium titanate is the same, is also rather boring and remains in a clustered state. And the same holds for strontium titanate. You see the tendency to form a homogeneous state, but it remains in an incomplete polar state embedded in a paraelectric matrix. This is opposed to barium titanate and lead titanate in accordance with the experimental data. And here's again the volume fraction, which tells you the same as on this side, where we have the length scale as a function of temperature. We calculated the dielectric response as a function of temperature and frequency. You see this here. I will just summarize this data with this one, transparency. So you see here the damping as a function of temperature for the 5 compounds. In agreement with experimental data, the damping in lead titanate grows when approaching the phase transition temperature. Europium titanate has an almost temperature-independent damping, whereas these two show or is close to the other 4 compounds. So this is the exception, which tells you about the first-order nature of the phase transition. Then we come to the oscillator strength, which is increasing with decreasing temperature, not for barium titanate and europium titanate. And here's the soft mode frequency as a function of temperature, and you see these 3 extrapolate to 0 to negative, respectively close to 0 temperatures, whereas these go to 0 at the phase transition temperature. I come to a final, okay, so I cannot. No more. Yeah. So is it already 20 minutes? Oh, you are very strict in time. So just to conclude, it is obvious that the A site in the perovskite plays a fundamental role for the dynamics and also for the phase transition, just opposite to what one would expect if you know that PD hybridization effects are driving a polar instability. Thank you for your attention.
Okay, can the next speaker come right up? We
can have thinking about this in terms of the hybridization of the acoustic mode and the optical mode, when you're thinking about the oxygen 18 dope strontium titanate and the potential polar nanoregion formation there, would you expect the isotopic doping to shift the acoustic and the optical mode differently to cause a crossing, or is there? Yeah, so in the isotopically doped strontium titanate, the 018 doped strontium titanate, for example, how would that affect?
This does not affect the dependence of the 2 modes on each other. Mm-hmm. What you see, however, is that the optic mode goes soft indeed, but it does not play a role for the temperature dependencies of the 2 modes, so they remain the same. But strontium titanate, the oxygen isotope replaced strontium titanate, is also not a ferroelectric in the sense that it is truly ferroelectric, but it's something like also very inhomogeneous state.
Okay. Well, let's thank Annette again. Okay, the next talk is the link between Goldschmidt tolerance factor. Your updates are ready. Lattice and stability type.